Hello everyone. Today we will be presenting on our project Mini Google File System, which is based on the Python implementation. Next. We know that Google File System is a distributed file system and which was developed by Google in order to facilitate its data access and storage needs. Google used a large storage system spanned over thousands of commodity servers to implement this system. And why commodity servers? Because they were very inexpensive as compared to others. So as to make the whole system cost effective, because that is why commodity servers was the best choice at that time. Then this system actually provided great reliability, fault tolerance, replication, integrity, etc. So in this project, we have implemented this small Google file system, which is based on Python servers. Uh, and in this presentation, we'll see these servers and what are they like and how they work. Apart from that, we will be differentiating between the chunk sizes and which chunk size will be the best for the system. Again, for the implementation purpose, we have taken bytes for the file instead of megabytes to make the simulation a little bit simpler. And we have also added an additional security feature in terms of authentication to our program. In the end, we will demonstrate our project. One of us will be demonstrating our project. So over to you, Salil.
Hello, this is Salil Mishra. I'll be presenting the client server. So the client server is the interface between the applications which want to access the data and the data lake where all the data is stored. GFS has a large number of clients which operate concurrently and doesn't need synchronization between them. So a large number of clients can read and append or write at the same time without need of any extra synchronization. Client interacts with master servers for getting the metadata. It doesn't get the file locations from them. And it caches this information for a limited time and interacts with the chunk servers directly for many future operations. And the client interacts with the chunk servers for all the file operations like reading the file or writing the file. And the client server does not cache any file data. Next slide, please. Okay, so the client we implemented in our the client we implemented has three functionalities, mainly downloading a file, uploading a file, and removing a file, which can be executed by get, put, and delete with their corresponding file names. To enable this functionality, we need all the basic servers running, that is the master server, backup server, and the chunk server. To perform any functionality requested by the user, the client makes the request to the master server for searching its location or its metadata, and accordingly, the request gets processed with the metadata received from the client, and then the requested like the data is transferred or like the request is handled accordingly with the application. And now my friend Geet will tell you about master server.
Okay, good morning. This is Geeta Agarwal, and today I'll talk about the master server. So the master server is the central server, and it is responsible for storing the metadata of all the chunk servers. This metadata here is implemented as a series of dictionary and is short and gives low latency. So this helps in providing the information about the chunk servers in a very fast speed. And it also maintains a file table which stores the detail of all the files that are there and where they are stored. So initially, a client first initiates the communication with the master, and it sends its request for either reading, writing, or deleting a file. The master server then checks for the availability of the file, and if found, returns the chunk server ID onto which it is stored. So this helps to avoid the bottleneck by the master server, as the client can directly access the chunk servers without getting the master involved. And it also sends regular calls to the backup server to keep the backed up data up to date. So now let's see a little about the code implementation. So talking about read and delete first, as we saw that the master server receives the exposed read, exposed write, or exposed delete queries from the clients. So it then checks for the file's existence and returns its mapping. The mapping is basically the chunk server ID to the client, and the client then directly interacts with the minion. And as we see in the code, it has many getter functions to get information regarding the file table entry, the block size, the list of files, the minions, etc. So this ensures that the master server has access to everything it needs and it can assist the clients accordingly. Now talking about the implementation at the write command. So for the write operations, it is also responsible for calculating the number of blocks or the chunks that are needed for writing the file. And it is calculated using the calc num blocks function. And it also allocates the memory for it using the alloc block function. So as we see in here, it initially checks for the existence of the file and then calculates the block size by taking the ceiling of the question or by dividing the given file size with the set block size. And while allocating the blocks, the new blocks are appended to the given destination or the previous blocks, and a new block ID, a new chunk server ID, and an index is randomly assigned to each block. Now we'll see a little about the next server.
Okay, so now I will be speaking about chunk server and how we implemented them for our simulation purpose. Chunk servers can be seen as workhorses of Google file system. It can be easily guessed from the name itself that chunk servers are responsible for storing chunks. In original GFS implementation, these chunks are stored on local disk as Linux file system. But in our implementation, we simply divide the text file into chunks and directly store them as small multiple text files. Also for our simulation purpose, we have only used 2 chunk servers, but it can be increased accordingly. Like Richa mentioned, we have used bytes as units of chunks rather than megabyte. Reason for same was simple, as we weren't dealing with big files in simulations. Okay, next slide. Okay, now let's see implementation of methods of chunk server. Like Geet have mentioned, when the client performs put or write operation, it first sends file to master server, where master server divides the files into chunks and allocates the unique identification number to chunks and then send them back to the client. After that, client calls the chunk server's put method. We have exposed this method so that they can be called by different servers and client accordingly. After receiving the data in chunks and their unique identification numbers, chunk server opens a file in local GFS root directory and saves chunks into it with UUID, that is a unique identification number assigned as a name of the chunk. Similar action happens for the get or the read action. Okay, next slide. Okay, since these chunk servers are low commodity hardwares, there is a good chance that at any instance of time, at least one chunk server will be non-functional. So to prevent data loss, many replicas are created. Since we are only using 2 chunk servers, a replica of each chunk is created and kept at both the servers. Here you can see while client performs put operation, after one chunk is written into one server, that server checks if there is any other active chunk server on the network. If there is more, then it forwards the same chunk to all the connected servers. So the put method happens in sequential action rather than by locality. Unlike first, whole chunks of a file is written into single server and then replica creation is performed. One minor issue in our implementation is that these chunk servers don't send heartbeat messages on regular interval to keep master server updated. Instead, every time when client performs certain action, master server searches for active chunk servers on the go and then proceed with the action. Now, Rita will take over.
Hello, so I'm Ritaya and I'm here to speak on the primary backup server. So as the name suggests, it's the backup server which acts in case the master server fails. So in our simulation, what we have done is that initially we have to load the backups. We have to execute the backup server first, which will read the existing file table, which is stored in a JSON file. And it will deserialize the JSON file into a string. And then the master server is executed. So the master server retrieves this JSON string from it. And so I'll just explain how it performs further. So then the JSON file, then the master server does all the actions as commanded by the client side, that is put, delete, or just list, and it stores the changes in a temporary JSON string. In case the master server dies or the master server shutdowns, it sends a request. It sends a request to the backup server that it should write the changes to a permanent JSON file, so that upon the next initialization, that JSON file can be read. So I have explained the functions. We can see the code. Next slide. So in this code, we can see that in this code, we can see that when the master server faces an interrupt, we have defined an interrupt function. It's interrupt handler. So it sends all the temporary changes stored from all the client interactions in a string, and then it converts it into a JSON string, and sends it to the primary backup server through the functions update file table on line number 20. And next slide. And in the next slide, we can see that when we get the update file table from the master server, the primary server makes the changes into the permanent file, that is the JSON file, which maintains which all files are stored in which all chunks. So this is the data flow. And next slide. And so one of the disadvantage of this is intentionally we have put that in the real world scenario, if the primary backup server is shut down, then there are many reroutings to point to next backup server. So in this case, there is only one primary backup server. So in case the primary backup server shutdowns, then all the changes made by the master server would be in a temporary JSON string and wouldn't be stored in the permanent storage. So the next time we initialize our system, then we cannot see the changes that were made by the client side. So now Rachna would tell us about the data flow.
Okay, so concluding what everybody has spoken about their own servers, I would like to mention how the flow, how the control goes from one Python file to another. Since we, as I could conclude from before, that first the client, can you please go to the next slide? Okay, so first of all, we come to know that the client.py file, that is the client server, basically sends a request along with the file name to the master server for it to check if the file exists in the list. If the file exists, it successfully acknowledges to the master server successfully acknowledges the presence of the file to the client server by sending a block ID where the chunks of the requested files are stored. Now, once client has received a successful acknowledgement, the client server would then request the chunks.py file, that is the chunks server, along with the block ID and the kind of command that it wants to execute. For example, if it wants to execute a put command or it wants to execute a delete command, so that is sent to chunk server. We have already seen the working of a chunk server, and finally, after completion of the command that is requested by the client, the chunk server sends an acknowledgement about completion of the program. So this concludes how the data flow goes on between the different servers. Now there is one little change from the actual simulation, that application of the Google file system, that instead of looking for the nearest replicas, we simply make requests to the block IDs that is returned from the master server. Could you change the next slide, please? Okay. Now I would like to talk a little about the additional user authentication feature that we have mentioned before. Now, first of all, the very first stage is that a user needs to be authenticated for requesting of execution of any of the functions. Now here we have a snapshot of the code from authentication file that we have written. We see that for user authentication, we have simply tried to include two fields, the username and the password. Now, since passwords are sensitive information and prone to attacks, so it was not advisable to store the passwords in plain text. Hence, we have used MD5 hashing to hash and store the password. Now, when we take a look at the code, first of all, it takes the input, it processes the password and stores the hash of the password in a hashed pass variable. Now, first of all, we check if the username that is entered exists in the system. If it does not, it simply returns invalid username. If the user exists, then we match for the passwords. Now here we see that on a successful login of successful authentication of the user, we return the value 1 in the client server. Otherwise, we return a value -1 in the acknowledgement that is sent from the authentication to the client server. So that's all. I would request Richard to take over from here.
Thank you, Rachna. Okay. So after listening to all the servers, we understand that the size of chunks is a crucial part of Google file system. And as you know, the size of a file is being stored in the real world varies from hundreds to thousands of GBs. So it becomes very difficult to store a single file on a single server. Hence, these files are subdivided into multiple chunks, each of a fixed size, and are spread over multiple chunk servers, which Sanchit already explained. Now, in order to compare the behaviors and to find the best out of these given chunk sizes, the block size of 32 MB, 64 MB, 128 MB, and 256 MB were taken by us by manually changing the block size to the required size in Google, gfs.conf file. Next slide, please. Here we can change it manually. Next slide. Yeah. So we can see from this table that the time taken to upload a file decreases as we increase the chunk size, implying that the larger the chunk sizes are, the better it is as an option. Next slide. Yeah. So one reason could be that there will be a reduction in master client interaction, and there will be a reduction in the size of metadata stored in the GFS when we take the larger files. Okay, and there will be a reduction in network overheads also when we take larger files. But again, there will be some disadvantages also. When we take larger files, there will be some internal fragmentation happening. And again, if we take smaller chunk sizes, then these chunks may become hotspots if many clients were requesting for the same chunk, and the data access will become even more convenient and easy for a user. So after counting all the pros and cons, it came out that taking 64 MB, like 64 MB of chunk size is the most reliable option among all the others. And therefore, Google file system also, the developers in there also took 64 MB as the standard option. Now, I'll be okay.
So this is the demo of our project. So first we will check for the chunk size, that is 256 bytes. So as we saw in the slides, we can change our chunk sizes. So currently it is 256 bytes, and we can see that in the right hand top corner panel, we have our primary backup server running. In the bottom right corner, we have our master server running, and in the bottom left corner, we have our chunk server running. So then first we can check, we can see the admin functions that we have written. So we have a create user list delete. just for the sake of it, we are seeing the list. We can see which all users are already registered. And now let's check for the current files which are there in the permanent GFS, permanent JSON file that we have stored. So for that, we can use the list command, and we can see that we have made one text file, that is sad.txt. And now if we want, now we can put another file of 30 KB. We can upload it to the GFS server. So for that, we can use client server. We will use put, and our 30 KB file is the random.txt. So we will store it in test.txt. For that, we will authenticate. And as we have issued the debug mode, we can see that it has been hosted on all the chunk servers, and the time it required was 4.06 seconds. And to check, we can see that whether it has been hosted. We can use the list command, and we can see that test.txt has been uploaded. Now, if we wanted to delete this file, so we can use we can use the command delete and the destination file, the name of the destination file, so test.txt, and we need to authenticate for that. And we can see in the bottom left corner chunk server file that it deleted all the entries present on all the chunk servers, and the time required was 3.59 seconds. Now keep in mind that this is for the 256 byte size. And now let's change that. So for changing that, we will go to the gfs.conf file, and we will change this as 128, for example. Now the chunk size would be 128. So now we have to again host all the files. So first close the chunk server, then the master server, and we can see on the top right corner that the file table has been updated because the primary backup server was running and the master server ended. So closing this and again restarting all the servers. First, the sequence would be, first we have to initiate the backup server, then the master server, and then the chunk server. And now we can, for currently to check which all files are present in all the chunk servers, we will see that test.txt was deleted, so only sad.txt is remaining. Now for the same functions which were conducted for 256 bytes, let us do it for 128 bytes. So we will put, so what is the file, random.txt and test.txt, the same file name. So the number of chunks created this time would be double of the previous one, so it will take a little bit more time than the previous inference. And then we see that it took 8.14 seconds, which is almost double the previous one. And so, and this similarly, we can also delete the file, and it will also take double the amount of time it took previous time. So we can see that this request was generated to the chunk server, and so the chunk server deleted, and it also took 7.63 seconds, which is almost double the time of 256 bytes. Thank you. End of the video.